The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams. And today, I wanted to talk about a subject that is of growing concern among astronomers and cosmologists. And it has to do with what's known as the Standard Model of Cosmology. Basically, our understanding of how the universe fits together, how it works, as well as its origins and its possible fate. And specifically, the growing concern I mentioned has to do with whether or not this model is in fact the correct one. Now, this is hardly a new concern. As with any accepted scientific theory, there have been detractors and people who have raised questions and challenges to the Standard Model for a very long time. As long as it's been the predominantly accepted model of how the universe works, there have been those who spoke out against it and challenged it. Alas, these concerns and/or challenges may have reached a point of inflection thanks to discoveries made by the James Webb Space Telescope, the Dark Energy Survey, and the Dark Energy Spectroscopic Instrument. After decades of being the most widely accepted model of cosmology, new data is indicating that scientists could be wrong on a few key points in that model. But before we get into what those findings are, we first need a quick review of what the Standard Model of Cosmology essentially states. Basically, it's known as the Lambda CDM model. Lambda stands for dark energy, or the cosmological constant, essentially the force that is causing the universe to expand over time. CDM refers to cold dark matter, the prevailing theory of dark matter that states that space is filled with a mysterious invisible mass that accounts for roughly 85% of the total mass of the universe. Together, dark matter and dark energy account for 95% of the mass energy density of the universe. The remaining 5% is made up of ordinary or baryonic matter, which is the kind of matter that we can see. Stars, planets, galaxies, cosmic dust, asteroids, you name it. As for how scientists arrived at this model, that requires a bit of a history lesson. So please get comfortable and get ready for some serious name dropping. We start by visiting Einstein back in the early 20th century when he was putting his finishing touches on the theory of relativity. Einstein had already led a revolution in science in 1905, where he synthesized and crystallized a lot of experimental data and theory by proposing that light traveled at a constant speed in a vacuum, regardless of the motion of the observer or the source, while also maintaining that the laws of physics were the same for all inertial reference frames, which was a guiding principle of science and cosmology for hundreds of years at this point. Now, this theory, known as the special theory of relativity, was meant to explain the behavior of light, which seemed rather anomalous, because conventional theory dictated that, depending upon the motion of the observer and the source, the speed at which light reaches us would change. And this was based on Galilean invariance or Galilean relativity, which itself was used to describe the motions of the planets and how humanity was part of an inertial reference frame, aka Earth, not only rotating on its axis, but orbiting the sun. And that applied to the Copernican heliocentric model of the universe, which Galileo refined. He was able to show scientists of his day that, in fact, all observations of the heavens up until that point, the reason why they were inconsistent or failed to predict the motions of the planets was because Earth itself was moving. And so scientists in the late 19th and early 20th centuries, when measuring the speed of light, they found, much to their surprise, that the speed did not change based on the source and based on whether or not Earth was moving towards or away from that particular source. And whereas scientists prior to Einstein had suggested that this may be due to a mysterious ether that filled space, and was responsible for either dragging light, slowing it down, or moving it along, propagating it. All experiments to test the effects of this ether all turned up negative. In all cases, the speed of light was constant and consistent, to which Einstein had suggested instead that scientists were thinking about space and time all wrong, for which he proposed that scientists were essentially looking at the wrong side of things. Instead, he proposed a four-dimensional space-time framework in which time was not absolute or independent of motion and velocity, which is something that Galilean relativity or invariance treated as a given, and that time itself was relative to the observer. And that depended upon their inertial reference frame, it depended upon their velocity and whether or not they were accelerating. And he boiled this all down to E equals mc squared. Energy equals mass times acceleration towards the speed of light. And this theory, it had significant implications almost right out of the gate. Almost right away, scientists accepted his conclusions and his equations because they simplified everything. They were consistent with all the experimental results, and it did away with any extraneous explanations, such as the whole ether idea. However, the deeper implications, which were things that Einstein himself would expound on in subsequent papers, these included what's known as mass-energy equivalence. Because if you look at the equation, E equals mc squared, what emerges from it is the fact that energy and mass, if you switch them around in this equation, everything still remains balanced. So that, in fact, mass and energy are just flip sides of the same coin. And the other being the aforementioned four-dimensional spacetime concept, that space and time are not distinct, that they are in fact part of the same framework. And last, that the speed of light is involuble, meaning nothing can go faster than light, because, in accordance with E equals mc squared and the mass energy equivalence, it would take more and more energy to accelerate closer and closer to the speed of light, to the point that you'd have to generate infinite energy to actually attain it, and that your inertial mass in the process, which would just keep getting heavier and heavier as you approached it, would also become infinite. So neither proposition is possible, therefore the speed of light is absolute. And so from that, Einstein began, over the next decade, to attempt to reconcile his theory with gravity. Because, much like motion and velocity in Galilean relativity, scientists believed that they had gravity figured out too. And this was all summarized and crystallized by a previous great scientist, Sir Isaac Newton. But key to Isaac Newton's universal gravitation and his theories on motion was the notion that gravity emerged as a natural product of point sources of mass, and that the gravitational interaction between objects, this was an instantaneous force, and it depended upon the object's mass and their distance from each other. But as Einstein demonstrated, nothing in the universe was instantaneous. Light traveled at a set speed, which was absolute. So information in our universe and the physical forces that govern it, they do not arise spontaneously or instantaneously. They take time, travel. And so he began to rethink gravity as not a point source attraction between two objects, but rather an effect that massive objects had on the very fabric of space-time itself. And he was partly inspired by all the revolutionary work in electromagnetism and quantum mechanics that established that electromagnetic phenomenon, it works in terms of fields. So he began to think of gravity as a field. Similarly, he was inspired by the fact that gravity wasn't distinct at all from acceleration, which was a key part of special relativity. So he envisioned gravity as something that is exerted by mass, and it alters the curvature of space-time around it, causing any objects that are in its vicinity to trace that curvature and to be accelerated, thus altering their perception of time and also bending the pathway that light will follow around it. And this was confirmed shortly after Einstein put the finishing touches on his theory of general relativity, as it was now called. And this was done by the Eddington experiment, in which astronomers actually witnessed space-time bending by looking at the sun during a complete solar eclipse and noting that stars that were in the background that should have been obscured by the sun actually appeared visible adjacent to it. And this is in keeping with Einstein's predictions and also his field equations. Basically, the stars appeared to be exactly where his math and his numbers would place them at. And similar experiments have been carried out ever since, involving larger and larger massive objects, up to and including supermassive black holes. And they've all shown that general relativity is, in fact, correct. And experiments with atomic clocks have shown the same thing. Clocks that are in space and are less subject to Earth's acceleration from its gravitational field, they record time at a different rate than similar atomic clocks running down here on the surface of the planet. And so general relativity became fundamental to modern-day cosmological models. Interestingly enough, the existence of black holes was something that had been inferred long before any observations of black holes were possible, and it was based on Einstein's field equations yet again. In particular, the work of Carl Schwarzschild and Subramanian Chandrasekhar. They both worked with Einstein's field equations on general relativity and found that, theoretically, there could be a class of stars so massive that when they underwent collapse at the end of their lifespan, that they would create a gravitational object so compact that nothing, including light, would be able to escape it. Because the acceleration, the gravitational force that they exerted, would actually equal the speed of light. And by the 1950s, 60s, and 70s, these early findings would have significant implications as scientists were able to realize for the first time how prevalent and how massive black holes could get. But before that, something else occurred in the field of astronomy that left Einstein feeling a little deflated and astrophysicists and cosmologists very intrigued. And that was the revelation that the universe was in fact expanding. And this was something that two astronomers in particular noted, and these were none other than Georges Lemaitre, a Belgian priest, astronomer, physicist, cosmologist, and Edwin Hubble, an American astronomer, cosmologist, physicist, etc. Both of whom demonstrated, with improved instruments and observations that were available at the time, that those distant galaxies that astronomers were now able to study in greater detail, that they were receding from our galaxy. And the greater their distance, the more they were receding. And this contradicted Einstein's own views on cosmology, which he had been espousing at the time and debating with Georges Lemaitre himself. Because the way Einstein saw it, the universe was a static and eternal place that was not subject to any serious changes. And he was motivated to do this because it was his own general relativity field equations that implied that the universe was likely to be expanding, that space was a function of time, and the universe was therefore likely to be dynamic. And this was why, in 1917, he added a parameter to his field equations, which was denoted by the lambda figure, which he called the cosmological constant, which in his mind was a force that counteracts gravity, that kept gravity in check and ensured that the galaxies remained in a nice state of equilibrium, neither expanding nor contracting. But as his contemporaries observed, Depending upon the value of the cosmological constant, the universe could in fact be expanding. In any case, things culminated in 1931 when Einstein visited Hubble at the Mount Wilson Observatory where he was stationed. He looked over his observations and he declared himself convinced. He said that the cosmological constant was the greatest blunder of his career, and that in fact the universe was in a state of expansion. But as time went on and our observations of the universe reached farther and became a lot more detailed, scientists would come to believe that Einstein was more right than he thought, and more right than he wanted to be. In many cases, ranging from cosmology to quantum physics, Einstein was responsible for discoveries he didn't like. However, before that would happen, there were a number of discoveries made which Einstein, having passed away in 1955, would not get to witness. And these discoveries happened in what is known as the golden age of general relativity, which lasted from 1960 to the mid-70s, thereabouts. And one of the most groundbreaking discoveries of this time was the discovery of the cosmic microwave background. You see, one of the greatest implications or consequences of Einstein's theory of general relativity, on the one hand, and Hubble and Lemaitre's demonstrating that the cosmos is expanding, was the question of the universe's ultimate fate, but more contentiously, its origins. Because if the universe is in fact in a state of expansion, then astronomers naturally ventured that at one time it must have occupied a much, much smaller volume of space. And this led to what is known today as the Great Debate. And on the one side, you had people like Lemaitre and Hubble, who argued that the universe began as a single point in space, as a singularity from which all matter and energy were created in a giant explosion, which gave rise to cosmic inflation, the birth of the first stars and galaxies, which came together to form the large-scale structure of the universe as we see today, which continues to expand. On the other hand, you had proponents of the steady-state hypothesis, which stated that not all matter and energy were created in a single event, and that new galaxies will emerge all the time in the universe as time and space continue to grow and expand. And to people on this side of the aisle, the other side was known as the Big Bang hypothesis crowd. And this was meant as a bit of a playful pejorative, but interestingly enough, the name stuck. Furthermore, they also believe that proponents like Georges Lemaitre preferred this theory due to, in part, religious bias. Georges Lemaitre was a priest, and therefore the idea of a single creation event must have sounded like something out of Genesis. However, neither side could produce evidence that definitively showed that their interpretation was correct until the 1960s. A key point in the whole debate was that if the universe emerged from a Big Bang, that there would be some relic radiation left over that would be visible in all directions, and by measuring the time it took that radiation to reach Earth, astronomers would be able to put accurate constraints on the age of the universe. And this is precisely what happened by the 1960s, when astronomers who had been looking at the universe through microwave filters to identify cosmic sources of microwave radiation, they found a persistent signal that was coming from all directions, very, very faint, and very, very distant. And after a lot of follow-up observations and attempts to measure the radiation and the distance that it had traveled, scientists concluded that this was in fact the relic radiation of the Big Bang, which all but ended the debate. There are still proponents of the steady-state hypothesis today who will use inconsistencies between our theories and our observations to suggest their alternative model. Nevertheless, the Big Bang went on to become an established part of the predominantly accepted cosmological model. The universe, as this model states, began with the Big Bang and has been expanding ever since. Another key discovery to come out of the golden age of general relativity occurred in the 1970s when an American astronomer, Vera C. Rubin, for which the Vera C. Rubin Observatory is now named, observed a problem with spiral galaxies. In short, she noticed that the rotational curves of these galaxies, the speed at which they spun, especially the stars in their outer edges, was much more rapid than their visible mass would imply. And this built on previous work by Swiss astronomer Fritz Zwicky, who noted similar anomalies in 1933 when he was observing the Coma cluster, a large grouping of galaxies. Now, to explain this, both Zwicky, Rubin, and her contemporaries, they ventured that, in fact, there had to be more mass there that we weren't aware of. Because, in accordance with Einstein's field equations, the rotation speed of a galaxy is very much an expression of its mass, and if galaxies were observed rotating this quickly, then clearly they had to be more massive than they appeared. And this gave rise to the theory that the universe was filled with a mysterious mass that did not interact with normal matter via electromagnetic forces, meaning that it was not visible in visible light. And so the term dark matter began to enter into common usage. More than that, it became an accepted part of the most widely accepted cosmological model. Just like the Big Bang, there are proponents of an alternative theory known as modified Newtonian dynamics, which argues that the universe is not filled with dark matter, and that in fact gravity behaves differently on the macro scale. And here too, proponents of this alternative theory, they will reassert it whenever discrepancies arise in our current cosmological model and new discoveries are inconsistent with it. The next big contribution came in the 1990s, thanks to the deployment of the Hubble Space Telescope. And Hubble was the first of its kind, and it was able to do something that no other telescopes could do at the time. By making observations from space, it was able to avoid atmospheric interference, and therefore able to see farther and clearer than any instrument ever had. Initially, it pushed the boundaries of what astronomers could observe in our universe from roughly 4 billion light years to 10 billion. That alone was amazing. But thanks to the Hubble deep fields and ultra deep fields, it was able to push that even farther to 13 billion light years. Now, due to increasingly accurate and refined measurements of the cosmic microwave background and the distance that its light traveled to reach us, astronomers have come up with a modern and current estimate of roughly 13.8 billion light years, which essentially means that, give or take a few eons, the universe is just shy of 14 billion years old. Which basically means that thanks to Hubble, astronomers were able to visualize up to 93% of cosmic history and were able to track the evolution of galaxies and larger cosmic structures from that point right on up to the present. And this revealed something very interesting and unexpected. As we covered in a previous episode, which looked at the Hubble tension, the purpose of the Hubble Space Telescope, among other things, was to measure the Hubble metric, or the Hubble-Lemaitre metric, which is to say, the rate at which the cosmos is expanding, which is why the Hubble Space Telescope is so named. The problem was that up until this point, and certainly since, astronomers, astrophysicists, and cosmologists believed that the expansion of the cosmos was constant, which is why the principle that describes cosmic expansion is also known as the Hubble-Lemaitre constant. But, according to Hubble's observations, looking at galaxies that were the earliest galaxies in the universe that were actually observable in visible light. Astronomers obtained two rather different values for cosmic expansion. In the early universe, they obtained one value, whereas local measurements, which looked at more recent cosmic history, were quite another. And these two results basically indicated that the universe was expanding at a more rapid pace during the last 4 billion years of cosmic history. And interestingly enough, this led to a rethink of Einstein's cosmological constant. Because, as scientists had speculated previously, depending upon the value of the constant, the universe could be in a state of expansion. And this certainly seemed to be the case based on these observations, or more specifically, that the universe had been expanding from the beginning, but as large-scale cosmic structures got farther apart, the mutual attraction of gravity became lessened, and so expansion sped up. And this provided the last parameter of the Standard Model of Cosmology, represented by the lambda figure, as Einstein originally proposed. But of course, there's also the caveat that the dark matter in this model is cold, which is to say that it's composed of larger particles that do not move as rapidly as they would in the case of a hot dark matter model, where the particles are smaller and move more freely, thereby generating more energy, which has been the predominantly held view of cosmologists and astrophysicists, though of course there are dissenting opinions and new research may affect a transition in that respect. In summary, this is how our current understanding of the universe came to be. It combines general relativity with Einstein's speculation of there being a force that holds back gravity, along with key contributions by Hubble and Lemaitre and other astronomers that revealed that the universe is expanding, and the discovery of the CMB, which confirmed that in fact the universe was created through a massive explosion, aka the Big Bang, and it has been expanding ever since. And finally, there are the decades worth of observations that fueled speculation that the majority of mass in the universe is in fact not visible in the visible light spectrum, and that the mass energy density is overwhelmingly composed, 95% as noted, of things we don't see, not unlike black holes, which are invisible in optical light, but are discernible based on the effects they have on surrounding spacetime and all that matter they pull into a disk around them, which is accelerated to close to the speed of light and pumps out so much radiation that the center of galaxies that have supermassive black holes, they become brighter than all the stars in the entire disk combined. And that is how the Standard Model of Cosmology came to be, and why it is the most widely held view of how the universe came to be and where it's going. Which brings us to the recent revelations by Webb, which, as noted, revealed things about the very early universe, which is to say less than a billion years after the Big Bang. It revealed a number of what are known today as little red dots, and these were some of the earliest galaxies that ever existed, and which appeared to be highly compact and very red. And as we noted in a previous episode, the way Webb had observed more galaxies than expected in the early universe, which seemed larger and more populated by stars than expected, this already caused a bit of a shakeup in our current cosmological models. But the existence of these little red dots also presented a real mystery to astronomers. On the one hand, there were those who believed that they were very dense galaxies, large clusterings of stars, hence their apparent brightness. and that they were also filled with lots of cosmic dust, hence why they're red. And this is similar to what are known as dusty galaxies that have been observed in more recent cosmic history. Others, however, believe that the reason for these compact galaxies being rather bright was, in fact, that they were early examples of quasars, aka active galactic nuclei, which, as previously mentioned, are caused by a supermassive black hole at the center of a galaxy, which generates so much energy from all the infalling matter of gas and dust, which is then accelerated to close to the speed of light, that this pumps out all that bright energy. And between these two camps, there is yet to be a clear resolution, although it was recently suggested by a research team that both of these interpretations could be correct and that they represent different evolutionary stages of very early galaxies. So, on the one hand, you have the stellar only interpretation, where these early galaxies were packed full of stars, and this led to collisions of stars in the most densely packed region, directly in the center of the galaxies, which led to the formation of massive black holes, which on its own was known as the black hole and galaxy interpretation. And last, but certainly not least, in fact, perhaps the most profound revelation was that cosmic expansion during this time, during the first billion years after the Big Bang, was actually faster than it was by about a billion years later, which would indicate that cosmic expansion was initially fast, then slowed down, and began accelerating yet again roughly 4 billion years ago. And so, as we covered in the previous episode that looked at what Webb has revealed so far about the cosmos, this led some scientists to consider the possibility that there was something known as early dark energy. In the same vein, this revelation has caused astronomers and cosmologists to once again consider that dark energy may not be a constant force, but rather a dynamic one, and that it's subject to decay over time and has been subject to accelerations and slowdowns in the past, which also has significant implications for the fate of the universe that contradict what many previously thought. Prior to Hubble, astronomers believed that cosmic expansion would eventually slow down and the universe would contract, and the Big Crunch scenario emerged from that. Whereas after Webb made its observations that confirmed that cosmic expansion was speeding up, the predominantly held view became either the Big Rip or the heat death scenario. In the former, the universe would continue to accelerate in its expansion until eventually the fabric of space-time itself would be ripped apart. The heat death scenario is similar in that the universe would continue to expand until all the stars in the cosmos, even the red dwarfs that can live for trillions of years, would eventually wink out, and there would be no light, no heat left. However, if dark energy is in fact dynamic, then what is likely to happen is that the universe will slow in its expansion, eventually stopping, but it will not contract. Instead, all the stars in the universe will go through their main sequence phase, they will die, eventually the red dwarfs will wink out, and this will lead to what is known as the Big Freeze scenario. And this is similar to the heat death scenario, but with the caveat that the universe would not still be expanding at the time. And so, as indicated, this has led to a rethink of a lot of the assumptions upon which the lambda CDM model is based. Nevertheless, it still holds for the time being, and while it may be subject to tweaking and revision, it doesn't look like we'll be throwing it out anytime soon. In any case, thank you for listening, and be sure to tune in next time, where the topic will be interstellar objects, which have once again become a rather popular topic thanks to the ongoing investigations and observations of 3I Atlas, the interstellar comet which has exhibited some strange behaviors that has once again fueled speculation that it may not be a naturally occurring object, but an interstellar emissary, or possibly a derelict probe of some kind. We will be getting into that. We'll also be taking a look at panspermia, the theory that the ingredients for life are distributed throughout the universe by interstellar objects, such as asteroids and comets, and which may even apply to rogue planets and stars that get kicked out of their galaxies from time to time. And of course, we'll also have some more exciting interviews with researchers, scientists, and people who are at the forefront of aerospace and space exploration today. Expect all that and more in the coming weeks. And in the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.